Hi, I'm Gareth. Until about 18 months ago, we didn't really worry that much about our electricity consumption. Even after we got an electric car, to be honest, I was so relieved that our bills had come down so much compared to buying petrol that I didn't really think about it that much. But with the cost of living crisis and then growing awareness of the climate crisis across last year, started to think about it some more. And I was really taken aback when I realised that the average electricity consumption for a household our size, according to Ofgem, should be about 4 megawatt hours per year. And when I took a look at our bills, we were using about 7. So I wanted to go off and investigate. So the first place that I looked was our smart meter. These have been rolled out quite widely across the UK. We've spent about £6 or £7 billion on them so far, and these should be collecting the data that we need, right? Unfortunately, even though they're supplied with one of these, an in-home display, they're pretty much useless, to be honest. I mean, yeah, you can take a look and it will tell you what you're consuming right now or how much that's costing. You can maybe even look and see how much you've spent this week. But to be honest, it's just like a slightly fancier electricity bill. I don't really believe that anybody's using these things day by day to manage their consumption properly. So I needed to find some way of getting the data out of the smart meter so that I could understand it better. Yeah, amazingly, despite the fact that these things are ours and we've paid for them, it turns out this is pretty difficult. The first thing we looked at was a Hildebrand Glow stick. So this is a USB stick that you plug in, will talk to your smart meter, extract the data and upload it to Hildebrand's cloud. From there you can then download it back as a spreadsheet or look at it online. And you know, it's kind of pretty good because it gives you a better way to analyse how your consumption is going. And more recently, my energy supplier Octopus has sent us one of these things, an Octopus Home Mini, that more or less does the same thing. So we're off and we're starting to understand maybe across the day where the consumption is going. But the problem is it's still not really that useful. It's hard to look at the data that's in there and be able to separate out and understand what's happening on a device by device basis. So being able to answer questions like how much is my lighting consuming, how much is the fridge consuming, how much impact is there from the tumble dryer, it's still pretty difficult if you're just looking at things at the household level. So we went one step further and bought an Emporia View. That's the small device that you can see just to the left of our consumer unit here with lots of wires coming out of it. And what this thing does is it's wired into your consumer unit and it's able to monitor the current in every individual circuit in your household. It's a pain to install. And there's also a lot of dangerous live terminals and stuff inside your consumer unit. And so I got a friend of mine, John Bowles, who's a professional qualified electrician, to come and install it, and he did a great job. But having the View installed meant that we were finally able to get information on a kind of line by line, area by area basis. That meant that I was able to start drawing graphs like this. So this shows where the energy went in our household on Sunday the 8th of October this year. So it's early October weekend, it's quite grey, not a lot of sunshine, not a lot of solar electricity generated. We're all stuck inside. We've got the cooker going, we've got the washing machine and the tumble dryer going, we've got lots of computers in use and video games and stuff like that. So it's a fairly heavy consumption day. But now we're able to start seeing really where the energy is coming from and where the energy is starting to go. But it still requires a little bit more analysis. So it's easiest for us to think in terms of units. This is what your energy company will bill you in. These are kilowatt hours of electricity, and essentially think about it like it's a bucket of energy. Like you might have a bucket of petrol to put in your car that will get you to a certain distance. A bucket of electrical energy will allow you to achieve sort of certain things. Okay, it's a chunk, it's a slug of energy. So how many buckets did we consume and where did those buckets go? Well, on this day we consumed about 20 units. 4 of them were used by the tumble dryer. 3 of them were used by the cooker. Another 4 were used by other white goods in the kitchen. So that accounted for the best part of half of what we used on this day. And in terms of remaining use, another 4 went into computers. So the computer that I'm recording this video on, my kids have laptops and external monitors. 4 units went into there. and another 4 units went into other things with screens. So 4K TV downstairs, and there's a PS5 with an old 4K TV plugged into it. That again is kind of, it's really driving our consumption. What I haven't mentioned so far is lighting. So lighting accounted for 1 kilowatt hour, and this was quite surprising. Because we've had so much drilled into us about, save energy, turn the lights off. If you've got LED lighting in your house, it doesn't really matter. Okay, from a sort of saving consumption point of view, turning off your lights doesn't really matter. I mean, you shouldn't leave your lights burning, but so long as you've got LED lights on, managing when they're on and when they're off is not going to make that much of a difference to your electricity bill. The other thing that really doesn't come onto the radar here is mobile phone chargers left plugged in on standby and overall devices on standby. Now, I'm not saying that they don't all add up to non-zero consumption, but to be honest, you could spend your day unplugging and plugging in devices and switching them off standby, or you could put one wash outside on the washing line and not use the tumble dryer for that cycle. And I know what would give you a lot more benefit. It's reducing less use of the tumble dryer. So what have we learned from this? Well, we've learned that entertainment and computer devices are real consumption for us. So we've got to be careful about making sure that they're only switched on when they're in use and that we're using all power down and power off capabilities. It's saying that our power goes into things with screens, things with CPUs, and things with heaters in. So, cooker, the tumble dryer, that's kind of driving an awful lot of this consumption over here. And what that probably means is that we need to carry on finding ways to swap out that consumption. So in the case of the cooker, we are already using the air fryer a lot more. And that's about half of the energy consumption of the cooker when it's in full use. So that's one thing that we could do. And the other thing here is this tumble dryer consumption. We can, when this one dies, replace it with one with a built-on heat pump, which is more energy efficient. And to be honest, those are more expensive, but looking at this data, I think they probably pay for themselves really quickly. They're also going to have a significant impact on reducing our carbon footprint. So from a consumption point of view, now relieved, I think that at least we've got a handle on where our consumption is going. The other interesting thing that came out of this analysis was looking at where these units, these buckets, had come from. So about 50% of our consumption is from green sources. So that's grid solar, that's grid wind turbines, and that's nuclear. And yeah, I count nuclear as green consumption. About 25% of it on this day was self-generated, so about 5 kilowatt hours, just under, was self-generated. So not a very bright day, but nice to be in the last quarter of the year and still be contributing something worthwhile. And the final 25% was from dirty sources, so fossil fuel generated electricity, in this case in Britain most likely to be gas. So if we're trying to reduce not just our consumption but our carbon footprint, turning off things and not using them on the right hand side of this chart is going to make a difference, but doing whatever we can to get the sources of energy greener on the left hand side of this chart is just as significant. Now the challenging thing is that this really isn't under our control. The thing that's under our control is where we choose to cast a vote. So this is the grid cleanliness on the day concerned. It's running about 172 grams of carbon per kilowatt hour produced, and this needs to be a lot lower if we're going to meet our net zero obligations and keep climate increase to below 1.5 degrees centigrade. This needs to be between 50 and 100 grams of CO2 indefinitely. And the only way that we're going to achieve this is by casting our votes and voting for politicians who are going to invest in renewable energy, who are going to invest in the grid, and who are going to invest in nuclear power. It's as simple as that. We can't do anything else about this. What we can do is think about when we are going to pull from the grid, particularly if we've got a battery or we've got a car with a battery. What time of day we choose has a very significant effect on our carbon footprint. It's because this figure varies hugely across the course of the day. It varies because renewables come on stream at different times. Wind blows for your turbines, sun shines for your solar, but also consumption varies a lot. If we are in a peak consumption time, so early evening generally, we were going to have to be switching on dirtier and dirtier sources of energy. So if we in a household, if there's some way of us not consuming in that time, we are going to be consuming cleaner energy. And you can see on this chart that the range here is quite significant. At the lowest point, the grid's about 70 grams of carbon per kilowatt hour. At the highest point, it's over 200. So that's about a 3-to-1 ratio. You know, the difference across a 48-hour period, that's tremendous. So we can start to see the benefit of shifting our domestic consumption into the early hours when the energy is generally cleaner, and filling the battery then, and then just kind of pulling from the battery and the solar panels across the course of the day. So what we're seeing here, the blue is what the devices in the house actually used at that time. Whether or not that was coming from the grid or from the battery or from solar, that's what we were actually consuming. The red is gas consumption. So we didn't have the heating on at this point, but we were using the gas hob, and the boiler kicked in to heat the hot water tank towards the early evening. The yellow is solar, so that's on the same scale, that's the energy that our solar panels produced. So yeah, even though we've got a panel on every south-facing part of our roof, we're really only generating about a quarter of what we're using on this day. And if you take into account what heating would consume in the winter, and how little solar would get in the winter, you can see we're really a long way away from self-sufficiency and no real prospect of being able to get there. Now below the x-axis, I'm trying to represent the carbon footprint of the house. So this sort of dark grey area on the left-hand side that's pointing down, that's the actual carbon that was released on that day when we filled the battery from the grid. The brown bit under the gas consumption that's the carbon that was released by burning the gas in the boiler. And the light grey bit is what I'm calling shadow carbon. So shadow carbon is what carbon would have been released if we had pulled from the grid at the time that we consumed. So we weren't using the battery, and we weren't generating with solar. So I'm trying to track that because hopefully the shadow consumption is bigger than the actual consumption, and that we are saving our we are saving our carbon footprint. And on this particular day, we generated a saving of about 40% compared to what would have happened if we hadn't done the solar and didn't have the batteries, which is nice. But the other thing that's in our control is when we choose to fill the battery. And there is a lot of variation there with the cleanliness of the grid across even the 6-hour period when our electricity is cheap. Only takes about 2 hours, just over, to fill the battery. So when is the cleanest 2-hour period in our 6-hour block of cheap electricity? That is when we should be charging the battery. On that graph I showed you earlier, the variation is about 30 to 40% across that 6-hour cheap period. So it really is worth thinking about, because over days and over weeks, this will all start to add up and be a more and more significant shift of our and reduction in our carbon footprint. So that's what I'm going to look at next, and hopefully have something interesting to share with you on the next video. But for now, that's it. My name's Gareth, and I will look forward to seeing you next time.